And we can go ahead and broadcast here. And we should see some attendees coming in soon. And I'll wait for Max to get back.
Yep.
I'm heating up his coffee. Perfect, we've got Max back. Well, I'll just go ahead and get started as far as an introduction goes, getting the webinar underway here. But just wanted to thank everyone for joining us for the virtual summit presentation. This one is titled Quantitative Reasoning with or Without Integrated Algebra. My name is Laura Shevlin, and I'm an educational courseware specialist here at Hawks. And today I'd like to introduce our speakers. They're Professors Max Aeschbacher and John Anderson of Utah Valley University. Professor Aeschbacher is an associate professor in the Developmental Mathematics Department at Utah Valley, and he's taught developmental courses for over 15 years, but recently his teaching focus has shifted to quantitative reasoning. In his spare time, he enjoys hiking, video games, and competing at bridge tournaments. And Professor Anderson is an associate professor in the Developmental Mathematics Department, also at Utah Valley University. He began teaching in 2007 and has taught quantitative literacy courses for the past 3 years and enjoys teaching non-STEM students. His research interests include studying how students learn math and the intersection of technology and teaching. We're excited to have you guys here with us today. And if you all attendees have any questions at all during the webinar, please enter those into the Q&A boxes located on the panel at the top or bottom of your screen. And we can address those at the end of the talk. But for now, I'll go ahead and hand it over to our presenters here.
Hello. Welcome.
Yeah. So just as we are getting started, we wanted to, come on, there it goes. This is a picture of our campus a little bit. You can see the mountains in the background, which are always fun to look at. And we want to spend just a minute talking about who we are. And so Utah Valley University is a regional state university. We have a couple of master's programs, but mostly serve undergraduates. In 2018, our head count was almost 40,000 students. And here at Utah Valley, we have 2 math departments, a math department that's the traditional one focusing on STEM majors. And we have a developmental mathematics department that focuses on developmental or remedial mathematics in preparation for the quantitative literacy GE requirement.
Quick word about this. We evolved out of a technical college all the way through a community college and a state college and into a university. And so part of the reason for having 2 math departments is historical, but we've really fought to keep it because it works pretty well for the students, we think.
Agreed. And of course, math in the state of Utah, math is a required portion of the general education requirement, and we really are focused on getting students to and through that requirement. And so we want to give just a little bit of history of math at Utah Valley University in our department. And we used to have a completion pathway that looked like the following. We started with an arithmetic course, to a pre-algebra course, to a beginning algebra course, to an intermediate algebra course. And after you finished your intermediate algebra course, we went with 3 different options: a quantitative reasoning course, a statistics course, and college algebra. And so this was our typical pathway, and this may seem familiar to some of you who have been teaching in mathematics for a while. And one of the things we found is that most students were taking college algebra to meet their GE requirements. And this led to the pathway that we have now, and we found that a lot of students were in this course even though they didn't necessarily need to be. So we have, over the years, we've had a lot of pressures to change the way we're teaching, to change the way we're interacting with students. In particular,
those of you who teach math out there probably know exactly what we're talking about.
Absolutely. 40% of the incoming freshmen to our schools, this is not just at UVU, this is across the state, we're registering for these developmental math courses. We had experimented back in the early 10s with an Emporium style course, allowing students to come in and work on where they were at. And we've had limited success with that model. And in 2015, the state legislature got involved, and we had Senate Bill 196, which said that any students who have an ACT score of 26 or higher on the math portion were automatically given GE credit. Despite this move, we did not see a decrease in students who needed to take developmental mathematics.
If any of you are out there fighting with legislators about whether or not it's right to teach developmental mathematics in college, I find I have pretty good success with the American argument. That is, what does freedom mean in America? It means that you can change careers when you want. It means that you can screw around in high school and still go to college. And as an open access institution, it's part of our duty as Americans to provide that service.
And so coupled with all of this, we also had an administrative push to shorten that sequence that could take a student up to 2 full years, 4 semesters before they even got into their GE courses. So we also have an expiration issue at our university where prerequisite math courses are only valid for 2 years. And this is true across most of the state. There's a few institutions that have a 1-year prerequisite, meaning that you need to have enrolled in the next course before that time period is elapsed, or else you're not going to be able to take that course. And the reason that this prerequisite exists is because we find that students retain very little of the algebra that they learn in college if they're not actively using it. So Max, you want to go ahead and talk about the attitudes towards math?
Yeah, so this is something that I started thinking about when I first started teaching full-time, and I realized that the reason students don't retain algebra is partly because they don't like it, and partly because they don't use it. And those two things are very closely connected. If they like math, they are more likely to use it when they need it. And if they understand it well, then they're more likely to like it. So I've been talking with my colleagues for years about how do we start shifting the focus of what we teach toward things that students are going to like and things that students might actually use. And it got harder and harder as the years went by to answer questions like, when am I going to use rational expressions in real life? And yeah, I can show them some contrived examples about where those things show up, but the answer is you're not. And so the goal was to take this quantitative reasoning course and refocus it with a new remedial pipeline to get students learning more of what they want and more of what they're going to use and more of what they're going to like.
Yeah. And we also, so speaking of the traditional math courses, we found that traditional intermediate algebra course was typically too much algebra for the average student, for most students. In particular, non-STEM students struggled with the algebra in these classes, and we were including a lot in case they were moving on and if they were STEM majors. And again, this shows that the attitudes towards math were not changing due to our courses. We weren't having the impact that we wanted. We did a really good job of helping them through the pipeline and helping them meet the requirements for the classes, but students left most of our classes with the same attitudes they had coming in. And so our department responded to the pressure. And one of the first things we did is we created a new streamlined pathway that starts with pre-algebra, that goes to intermediate algebra, and from there branched into our 3 quantitative literacy courses. In addition, one of the things that we're going to be talking about today in a lot more detail is that we created a new co-requisite course that integrated algebra into the quantitative reasoning so that students could gain access to it directly from pre-algebra. And one of the really nice features of this is that most students now have a 1-year pathway to get through their GE requirement, their general education requirement. So this is our co-requisite solution, and we're going to talk about this in a lot more detail now. It's a 6 credit hour course. It uses just-in-time remediation so that the algebra that they need to be successful in a topic is presented right before that topic so that it's relevant to them. Students, again, come in at that pre-algebra level. We assume that they just have pre-algebra, no other algebra. And as mentioned, most non-science majors can be done with their math requirement in a single semester. And in fact, any non-STEM major, anyone who doesn't need to go beyond their quantitative literacy class, will be done with quantitative reasoning, and they can all be done in the first year if they work through the course.
A quick word, a quick analogy about that. In our unit, which is called University College, our department works fairly closely with another department called Literacies and Composition, which is sort of our English analog. And I watched what they were doing, and all of their remedial writing courses are writing courses. I mean, they do teach some topics, you know, about ethics and writing structure and stuff like that, but they mostly just get the students writing. And I thought back to what was I learning in junior high in terms of math and English? Well, in English, I was learning about sentence structure. I was learning about what nouns and verbs and gerunds were. And in math, I was learning, you know, pre-algebra and algebra, that kind of stuff. But when you get to college, the tradition in mathematics is to teach them all the same stuff that they learned in junior high and high school again. But in English, they don't do that. They don't say, what's a gerund? You don't ever take a test in a remedial English class talking about what nouns and verbs are and doing sentence diagrams. You just don't do that anymore. You just get in and write. And that's what this course is all about. Yes, we do some just-in-time remediation when students need a particular algebra topic, but mostly we just put an equation on the board and say, let's solve this. Because get in and get your hands dirty.
And so our next slide is the course learning outcomes. And we're not going to spend a whole lot of time on these, but the one thing that I do want to point out here is that there's no individual listing of algebra topics or math topics. It's more about the general feel of approaching mathematics and using mathematics. So explaining real world information in mathematical forms rather than dealing with, do they know what a linear model is or an exponential model is? And so,
you know, perhaps it could be argued that now more than any time in the history of humanity, is it important for your average layperson to understand what exponential growth looks like?
Yeah, we're witnessing one of those right now that I'm planning on spending some time with my students when I have them back next week.
Oh, I'm going to make a lot of videos about coronavirus, and given what just happened in Salt Lake City this morning, earthquakes.
Yeah. And so the idea is to give them the tools and the ability to learn and to use mathematical forms and to be able to read. So when they see a news report, they'll be able to understand it rather than just taking the assumption that the news report is lying to them in some way. They'll be able to know how, for instance. Coupled with our course learning outcomes, we have our 4 pillars that we require are taught. And so this is more of what a math teacher would think of when they're thinking of the learning objectives. So we start with stats and probability. We have our modeling of linear, exponential, and logarithmic models. We talk a great deal about financial math. And we spend some time talking about unit analysis. And these are the 4 pillars that our department has decided are the math that students learn in the quantitative reasoning course. In addition, there's typically just enough time in a course that the teacher has the ability to reach in and talk about some optional topics and be able to share some of their things. And this is, I think, one of the great things about this class is being able to individualize it to the student needs, to my desires, to what I like to do, and to show students that math shows up in more than just algebra.
John, can you go back one slide?
Sure.
The way I sort of map this out for my students is a little bit different than listing it sort of linearly like this. I think the pillars of the course are stats and probability, modeling, and financial math, and unit analysis is sort of the spine that runs through all of it. So I don't ever do necessarily a specific lesson about unit analysis, but I'm always telling my students to think about units and to use units as a guide for solving problems. If you combine numbers in a certain way that changes the units, make sure you're heading toward the units that you actually want.
Absolutely.
And I also had a comment about the subsequent slide. As far as these optional topics go, voting theory and apportionment are so relevant and so cool. And you get a chance to talk about US history, and you know, you can bring in even, I mean, I try to avoid strict political discussions, but it definitely sparks students' interest, and I just love it.
Yeah. In fact, the very first time we taught this course was in the lead up to the 2016 election.
You know, such good timing.
It made for some really interesting conversations about how people vote, why they vote, how they should be counted, and different things like that. And it was interesting to see the students' reactions to that across the gamut. From the young just getting ready to vote for the first time to the non-traditional students who've been involved for a while or not.
Mm-hmm.
And so we wanted to talk just a little bit about some curricular examples. And so the idea here with this one is we're talking about modeling. And so we want to see how modeling can be used for real life phenomena using algebra. The main focus is on linear and exponential, but we do get into some logarithmic as well. And we assume that students have a passing familiarity with linear equations. And again, this is where the majority of the just-in-time remediation occurs. We expect them to know y equals mx plus b and to have some passing knowledge of what that is and how that translates into graphs. But depending on the students, we may need to spend some time in remediation. So if they don't know these, or if they need to review these, as an example, when I teach linear, just before I teach linear models, and again, as I'm getting into the exponential models, I go over the Cartesian plane and help them understand how points work and what they are and how they relate to the equation of the line. And I also spend a good deal of time talking about the rules of exponents before getting into exponential graphs.
Tell me if you experience this too, John, but in my experience, if there's one thing that students remember from high school, it's y equals mx plus b.
Absolutely. They may not be able to explain what all the parts are, but they sure know what that equation is.
They might not know what the word linear means, but they know y equals mx plus b.
And when you can make that connection, it's awesome. It's fun to watch that light bulb turn on as they actually are able to do things with it.
Yeah.
So we have an example of some curriculum that has been used, and this is stuff that I share with my class, and it's interesting. I created this back in 2016, and it's interesting how relevant today it is. So there's a new vaccine and a good policy about the gamma virus, and the reported number of cases of the gamma virus infection has been dropping by 70% each since the year 2010, each year since 2010. And again, this is just an example that was made up. I'm not basing this on any real world data, although since I've made these initial slides, I have found plenty of real world data that could be shared as well, and I do in my individual classes. So back in 2010, when the vaccine was first being pushed out, there were 1 million reported cases of this disease. And if the present rate continues, the question is, how many reported cases of the virus infection can we predict will be there by the year 2016? And so I did this, of course, teaching in 2016, so I wanted the students to be able to talk about this in terms of where they were. And I want them to be able to make a prediction of when the virus will no longer be around. When will the vaccine have worked so that the infection rate drops to virtually zero and is no longer a concern? So in this example, we're dealing with negative growth. Instead of expanding and getting more populous, it's decreasing, but it's doing so in an exponential rate. So as a growth rate of minus 70%, which translates to minus 0.7. And of course, we need to convert that to a common ratio or base. So we simply add the growth rate to 1 and get a common ratio or a base of 0.3. The initial population, we were told, is 1 million infected people. And so our formula that we're going to use for all exponential models is that the current population is equal to the initial population times the common ratio raised to whatever generation or year we're looking at. So using this for 2016, we see that 6 years since 2010, and we're able to plug the 6 in and multiply all that out. We find that in 2016, there should only be 729 cases if we are following the model perfectly.
Okay, let's talk about how this fits in a co-requisite model for just a second.
Absolutely.
You don't need to do a huge lead up teaching students all the properties of exponents. Now, I like to go over the properties of exponents because I think that's important, but get in there, have them do the problem, and then do formative assessments, correct their mistakes.
Mm-hmm.
tell them when they're using a property of exponents incorrectly. And have them do homework. Homework is a big important part of this, and that's where Hawks is pretty helpful. The mastery based homework that they can do on these algebra topics tends to be pretty easy for them to do at home. They do it, they get their skills up to par, and then they can come into class and see problems like this and understand them.
And it's really fun too. One of the first things I do at the beginning of my class, just related to Max's comment, is get them used to the fact that they're going to make mistakes, and that's okay. And I make mistakes myself deliberately sometimes and sometimes not, and show them that it happens with everyone, and that it's the process of learning from those mistakes that really matters as well. And so getting them involved and getting them to try it can be very, very, very useful. And so I just show the next year it drops another 70% from where it was. So we're down to about 219, 220 cases or so. And we can see it continue to drop off in 2020 this year. If this virus had been affected this way, there'd only be 6 reported cases. And getting the students to see that is helpful. And of course, it's even more helpful to have them graph these so that they can see what the exponential graph looks like over time. And they can see that drop from year to year. Our next example, so this is an example of one that uses the just-in-time remediation. The next example is one of those optional topics. And Max, I'm going to go ahead and turn this one over to you. Given that you don't control the slides, do you want me to show the whole slide and then you want to
Sure.
talk about it there?
Yeah, that'll work. So sealed bids is one of those fair division methods that you can use to divide up, say, large discrete objects that are of different values. And the classic example of this is dividing up an inheritance. Let's click ahead a little bit. Yeah, so grandma has died and left her cabin, a Ferrari, a Picasso, I guess that's all, to 4 grandchildren. So you've got 3 valuable objects that are of different value, and certainly of debatable value, especially this Picasso. I mean, who's to say exactly how much it's worth? But she needs these to be divided fairly among 4 children. Well, you can't cut a Ferrari in half and have it be worth anything. So it's going to have to go to somebody, and you have to decide how to do it. And that's what sealed bids are all about. So the way they do this is the children all bid. They decide how much money they think each of these things are worth. So they make their bids, and I think we have an example of, who bid what for what. So Amos, for example, thinks that the cabin is worth $500,000, and so on and so forth. So you look at each of these bids and you can organize them in a table. I love to have my students do this using a spreadsheet, because I think it's really instructive and you get a chance to talk about some spreadsheet formulas, and that works out really well. So in the allocation, you just simply give the item to whoever bid the most for it. James thought the Picasso was worth $750,000. That's a lot more than anyone else thought. Okay. So James gets the Picasso. But then you need to look at each player's total. So Naomi, for example, thought that all the items together were $1,070,000, which means her share is 1/4 of that. Her fair value is 1/4 of that, and it's 1/4 because there's 4 players in this game. We don't care that there are only 3 items. There are 4 players, so she needs to get 1/4 of the bounty. So her fair share is $267,000, but she got nothing. Naomi got nothing. Go ahead and show that next slide. Since Naomi got nothing, she is owed $267,500 by the game. Each of the players got the items they got, and they got that much value. And in the case of Alex and James, they got more than their fair share in value, which means they need to pay that much cash back to the game. And once this is all done, you look at the net for each player. They pay that money back in, and then there's usually a surplus. So once the players who didn't get enough have been paid their fair share, and the players who did get enough have paid what they owe, there's a leftover pile of money, which in this case is $293,250, and you divide that in fourths and just give give 1/4 of it back to every player. Okay, so here's an interesting motivational question to ask the students, and you can all think about this yourselves. Why can't the surplus ever be negative? Why are we guaranteed a non-negative surplus? I think that's a really interesting question to think about the nature of the bids. And you can look at some extreme cases, like what if someone decided that this was the price is right and they decided to bid $1 for everything? How does that impact the surplus? Okay, so this is just a fancy arithmetic problem, but it's very rigorous and mathematical in nature. It requires organization of mathematical information using charts and tables. It requires genuine mathematical and logical reasoning and thought. And there are a lot of moving pieces to keep track of. And lastly, it's an example that everyone thinks maybe if they're lucky, they'll have to deal with. I mean, everyone wants to have a rich great aunt that they didn't know die and leave a bunch of money. I mean, not all of us are going to get that, but it can be a fun fantasy, even so. And even if we have a beloved ancestor who dies and leaves us something, it's nice to think about a way to fairly do it so that we don't have to fight about it. One of the drawbacks, by the way, to this example is that all the players need to have enough money to play. You can't divide an estate this way unless people actually have the cash to compensate the pot for the bids that they make. So there are some limitations, but it's definitely a great example of a rigorous mathematical topic that can be taught with absolutely no prerequisite material.
Absolutely. Our next division is a fair division problem. And I'm going to talk about this one. So fair division is a process that can result in a fair way to divide assets that can be divided, such as land, where we're going to cut it up and give different pieces to different people, or inheritance, or food, or things that you can cut apart. Like the previous example had the Ferrari, where if you cut the Ferrari in half, it's useless to both people. But if you have land, or if you have food, or you have other things that can be more finely divided, then there are other ways of dealing with it as well. And what's interesting to note is that all these fair division problems can be solved using a system of equations, but there are solutions that are based on arithmetic and quantitative reasoning instead, which is why we like these so much. So we could spend the time to talk about systems of equations, or we could give students a way to think about and approach these problems using nothing but arithmetic.
This was a watershed moment for me when I first started teaching quantitative reasoning. I realized that these students didn't necessarily have an expected background where they would understand systems of equations, but we started solving the problem, and it turned out that they had all the right answers about which way to proceed and what to do. And we never even used the phrase systems of equations. We just hacked away at it by brute force, and it was fun, and we got the solution.
So we're going to give a 3-player example of dividing up this cheesecake that has 3 flavors in it: chocolate, vanilla, and strawberry. And so Jim, Kevin, and Ed they purchased this cheesecake, and the cost of the cheesecake is $30. And here are their individual beliefs about how much each of the flavors is worth. And notice that for each player, it adds up to 30. That doesn't have to be the case, but it does make comparisons a little bit easier if they do it this way. And so Jim likes all the flavors equally. Kevin likes chocolate a bit more than the others and doesn't like vanilla that much, where Ed likes the vanilla the most and strawberry the least. And so this is the way that they approach this problem. They want to make sure that they're getting their fair share of $30 out of this. And so by chance, Ed and Kevin are randomly chosen to go first, and they decide to split the cheesecake in the following way. So you can see the green lines added to cut it off. So there's one that has all of the vanilla, a little bit of strawberry, and about half of the chocolate. And the other one has the rest of the strawberry and the other half of the chocolate. So this is what Kevin gets on top, and this is what Ed gets on bottom. At this point, Jim enters the game. And before he gets involved, Kevin and Ed have one more step. They need to take their share and split it up into 3 pieces, because there's 3 players now, so that Jim gets to pick 1 piece from each of them, and they're left with 2 pieces. So we're going to start with Kevin, who happens to have $15 worth of the cheesecake to him, consisting of half of the chocolate and 84 degrees of strawberry. And it's helpful to think of this in terms of degrees. There are other ways of doing it, but thinking of it in terms of degrees helps the students realize what's going on. So he needs to split into 3 pieces that are worth $5 each. And he does that by making some calculations. So that he has $8 of the chocolate, since he had half of the chocolate, is worth 16 to him. So he's going to carve off $5 of that using the following proportion. And when he solves that, it shows him that he has 37.5 degrees of chocolate cheesecake is worth $5. So there's his first share. His second share he does using the same thing, but he's going off of the strawberry instead, which has a different value. And when he calculates that, it comes out to 60. And it turns out that the remaining strawberry and chocolate each add up to $5. So he has now split his perfectly into 3 pieces, and he's ready to go. Jim now looks at all 3 pieces and uses the same proportional reasoning to evaluate the price of the piece. And so for slice 1, it's worth $3.13. Slice 2 is worth $5. And slice 3 comes out to $3.88. Well, as he's looking at this, he's obviously going to pick the one that's worth the most to him. So he's going to take slice 2. Ed does the same thing using the same reasoning. He has $21.50 though, and so when he divides that by 3, he finds that each piece is worth $7 and approximately 17 cents. And it's harder, but it can still be done, and it's done using the exact same method. So for his first cut, he's going to take all of the strawberry, because that's only worth $1.50, which is too little, and $5.67 of the vanilla. And when he does that, he calculates that degree, and he's able to cut that much. He goes to the next one, and because there's still enough value left in the vanilla and just the vanilla, he can get a piece that's purely vanilla. And that leaves his third piece, which we double check, and sure enough, it comes out to $7.17 as well. So now that he has his 3 pieces ready to go, Jim gets to come and take a look at them. And again, they're all equally weighted for Ed, so whichever piece Jim takes, Ed's still getting 2/3 of what he has available to him. So he evaluates them one at a time, and slice 1 is $6.78. Slice 2 is just $4.78. Slice 3 is $6.44, and again, he wants to pick the one that's worth the most, so he's again going to take slice 1. And now we can see that here's Jim's 2 pieces, worth $11.78. And Kevin gets a total of $10, and Ed ends with a total of $14.33. And so this example is showing how we can use proportions arithmetic and have everyone show up with getting their fair share of the overall cheesecake.
So fitting this back into how it looks in a co-requisite course, sharing cake in this way is maybe not something that people would do. They would just be friends about it, and they'd say, okay, you know, let's just share the cake. But it's a fun theoretical exercise to look at how it would be done exactly fairly to make sure that everyone gets a fair share. And with very basic prerequisite knowledge, you need to know about how many degrees are in a circle, and you need to know you need to have some functional understanding of proportional relationships, and relative percentages maybe come into it a little bit too. But it's a really fantastic example.
And on this, it was funny because when I happened to be putting these slides together for my original presentation with my students, my wife and her sisters were arranging for a trip to a county fair where families could buy a pass that came with so many coins, and the coins would allow the kids to play the games. But we had different sizes of families. I have 2 kids. One of her sisters has 8 kids that were all going. Another one had 5, and the last one had 3. And so we all paid the family price to get in, but they redistributed the coins based on the size of the families using this proportional thinking exactly. So it was really interesting to see it happen while I was preparing to share it with my students.
Okay, I'm trying to keep an eye on the time and make sure we have time for questions. How many more examples do we have, John?
We've got the apportionment, which we might want to just skip over and go straight to the installment loans. Unless you want to do apportionment and skip installment loans.
Let's do apportionment because that's more likely to be one that people haven't seen before. Math teachers out there kind of know how installment.
This one's all yours.
Okay.
The slide's fully updated.
So the United States the founding fathers said the United States Congress should be apportioned among the states according to their populations. And it was sort of thought when this was written that this was going to be some sort of easy arithmetic problem, but it turns out this is a very complicated arithmetic problem. And it leads to a lot of weird paradoxes and bad feelings, potential for bad feelings, potential for states feeling like they got punished even though their populations grew. And of course, the applications for apportionment go beyond just apportioning seats in Congress. You could talk about like what John's saying, tickets to a carnival or a movie. Or just apply this to any situation where you're trying to divide up discrete objects among people or entities like states. So let's imagine that we've got this interstellar federation consisting of 5 planets. Ariel, Beaumont, Haven, Lilac, and Cento. We've got 115 seats to apportion, and we're going to do this by their population. So how do we do it? Well, if you ask the founding fathers, they won't agree. Hamilton had a method, Jefferson had a method, John Quincy Adams had a method, and there have been a couple of other methods popularized since then. The method the current US Congress uses is called Huntington Hill. But all the methods agree about this. The first thing you need to do is compute the standard divisor. The standard divisor says, take the number of things you're trying to apportion and divide that into the total population. And this will tell you roughly how many people correspond to one of those things. So in this case, we're talking about seats in a Congress. It's about that many people, whatever that number was. Then we need to compute the standard quota. So take the standard divisor and do what the name suggests, divide it into the population for each state to figure out approximately how many seats each state should get. So for the first one, we had the 26.49, 39.45. And here you see the problem. These are not integers. So we've got to do something. We've got to account for this somehow. Are we doing Hamilton's method here, John?
This is just simple rounding.
Okay. So if we were to just round these numbers to the nearest integer, so 26.496 rounds down to 26, and so on across. Okay. Well, that adds up to 113. We've got 2 seats left that haven't been accounted for. So what do we do? Well, I'm sure every state could make an argument that they want those extra seats. And conventional rounding almost never gives you an exact apportionment, so we have to do something else. And that's where apportionment theory really gets interesting. What do we do, and what impact does the choice we make have on future situations? So that's something I like to have a lot of fun with in my classes. And again, it's a great example of something that can be taught in a co-requisite type course, because you need very little prerequisite knowledge. If anything, knowledge of US history is as useful as prerequisite knowledge of mathematics. It gives you an opportunity to talk about representing and reading and understanding math using charts and tables, because it makes a lot of sense to put this into a spreadsheet. And you can do it with hardly any prerequisite math.
And the students really seem to get into it as well.
Mm-hmm.
All right, so I'm going to skip over the next 2 examples just for the sake of time, because we wanted to talk about the impact that this has had on us. So we have an example of financing a car, and we also have one for expected values, buying insurance.
Yeah, I love to talk about expected value of insurance. That's one of my favorite examples, but it's worth skipping here, I think, because we want to talk about assessment.
And again, all of these, we have that just-in-time remediation where we may review a few things, or based on the way that students are approaching the problems, we may come in and help them correct their knowledge and be able to use the appropriate terms. And so here you can see the historic pass rates for our 1030s, the quantitative reasoning course. And you can see that we started in the fall of 2017 with our 1035, our integrated algebra course.
So 1030 was the old quantitative reasoning course?
1030 was the original course. And in this, you can see in the fall of 16 here is when our department took over this class. Before that, it belonged to the other math department. They had all of the quantitative literacy courses. In 2016, the choice was made to move it over to us. And we just didn't have the data for the other entries at the time that I pulled this data. But you can see, I think one of the interesting things here is the similarity in the pass rates between the two courses now that they've both run for 3 semesters.
Now, this is a perfect example of the kinds of charts and graphs that our students would maybe be able to get the right information out of and ask the right questions about, because you can see by looking at this graph that it's not quite telling you the right thing, because the dark blue line is pass rates for 1030, and this lighter blue is pass rates for 1035, which encompasses at least 2 semesters worth of course material. So to have a pass rate here that's comparable is pretty substantial because it's representing 2 courses worth of progress. The blue line only talks about 1030. It doesn't talk about any prerequisite algebra courses that these students have taken.
Absolutely. Our next slide is another one that we've had run, and here we're talking about the impact that Max was just speaking of. How much time, how many semesters have been saved, and how much money has been saved in tuition by having a single course rather than spreading it out over 2 courses.
And this is another good thing to compute if you have any interaction with legislators or administrators. They love to talk about money saved by students, and they love to talk about tuition savings, especially for a regional state university like Utah Valley. If we talk about $434,000 in tuition savings for students, the legislators know that the state of Utah pays about half of the costs of educating these students. So that doesn't just represent $434,000 in tuition savings for students. It represents close to $500,000 of tuition tax savings from the state.
Because this was calculated just with what the students pay, but again, with the state paying about half of it, it does encompass a lot higher money saved. We also are working on assessment for our courses, making sure that we're teaching the right things, that our students are actually learning what we're hoping for them to learn. And so we have done a couple of trial runs, and I want to talk about one of these. So this was in the fall, or no, this was last spring, wasn't it? This was in the spring of 2019. We asked all of our 1030 and 1035 instructors to give their students the same question about expected value. We then collected all of those, including all of their work shown and anything that they had to write or say about the problem. And we selected 100 of those tests at random using stratified random sampling over the type of course, whether it was a concurrent enrollment course or our just quantitative reasoning course or our quantitative reasoning with intermediate algebra. We took 20 of those tests and had 4 graders grade them. We met together, and then we compared our scores to ensure that on the rubric that we were using, everyone was within 1 point, and we knew why. So we used this to help everyone become familiar with the grading process so that we were grading similar ways. And the remaining 80 tests were distributed. Each person got 20 of them, and then they went through and graded those their own 20 tests on their own. We took this information and ran it through some one-way ANOVAs, and just some general comments. It looked like our concurrent enrollment students performed better than the students in the non-co-requisite class, and our co-requisite students also performed better than the non-co-requisite class. And we're going to show some numbers here and some graphs to try and explain that. But it did appear that the high school students who took the course, the non-co-requisite course, they had a longer time period, and other factors may have influenced that. But we were quite thrilled to see the co-requisite students able to perform at or better than the students in the non-co-requisite. So you can see them here. We had different objectives that you can go back to that course objective. We wanted it to be a handout. And so we'll make that available with the presentation when it goes out as well. So you can go back and map these, but talking about the different objectives that we were asking students to do, such as being able to convert information into relevant forms to use, and being able to calculate the results correctly, and being able to analyze real world data. So this was an expected warranty problem. What is the expected cost for getting a warranty? And we looked at this, and you can see the overall means, and this is on a 4-point scale, 1 being the bottom end of the rubric, 4 being that they perform admirably, that it is very elegant and very easy to use. And you see our students hovered right around the 2, which is 3 is the proficiency. This is just below proficiency. They're able to talk about things, they're able to do things, but they're not quite at the level we were hoping for. And you can see the different breakouts. A 0 is given if they left it blank.
Yeah, 4s would be pretty hard to get because a 4 represents the kind of solution that a typical teacher would write on their answer key.
Right.
It's mathematically correct. Everything's correct. It's accurate. Comments are insightful. 3 is really what we hope for most of the best students, that just can come up with something that's correct. And a 2 is a little bit below that. So, I mean, this was not necessarily an easy question. It talks about expected value in a fairly complex scenario of a cell phone warranty where there are different things that could happen to the phone, like the screen could break or the phone could be destroyed or stolen. And these outcomes have different costs associated with them and different probabilities associated with them. So these results are not quite what we wanted. They're a little bit low. But the concurrent enrollment, it was very interesting to see that the concurrent enrollment numbers were so much higher.
In fact, it's a little bit easier to see on our graphs where you see 1030 is always the one on the left, 1035 is in the middle, and the concurrent enrollment is on the right.
Yeah.
So quantitative reasoning, integrated algebra, concurrent enrollment.
So for objective 4, actually, it looks like 1035 did slightly better than concurrent enrollment.
It did.
But we had some possible explanations for why this could be. One was that the concurrent enrollment teachers taught this course over a full year instead of just one semester. So the students may actually just walk away with better understanding just from having extra time. 2 is the test questions were made available to the teachers before the test. So it's possible that the concurrent enrollment teachers were teaching to these questions. And there was one more. What was it, John?
It could be that because they're taking the concurrent enrollment class in high school, they may have been a higher caliber student to start with.
Right. We have that confounding variable that these are likely just a higher quality population of students.
And none of those were controlled for, and we're trying to find the right ways to control for those as well. But,
yeah, I mean, separating the data is a good start, but it would be interesting to figure out to do that, yeah.
And so our next steps in our assessment plan is we're expanding to include all 6 learning objectives rather than just the 3 that we had before. The questions on the final would now include 1 major question from each of the required content areas that we talked about before, those pillars. And we were going to maintain the free response question aspect to it because we wanted to see students' thought processes, not if they could select the right option from a multiple choice test. In addition, we recommended to all teachers to increase the project and written work requirements in all their courses. So they weren't just doing homework, they weren't just doing math, they had to explain their reasoning, they had to put things together in different ways. And in fact, some of our faculty have decided to move towards a completely project-based course with this, but that's not universal yet by any stretch. We also
I want to mention,
go ahead.
This co-requisite model for quantitative reasoning fits really well with an entirely project-based approach. The design works well, and it would be fairly easy to implement. We've got faculty doing it. It also fits well with a flipped classroom. John has flipped his classroom completely, and that's how he's been doing it for a couple of years now, and it seems to be working really well for him.
It does.
So the flexibility of this model sort of goes across all teaching styles.
And again, just coming back to it, we asked all of our teachers to focus on the higher order learning from Bloom's taxonomy rather than just the rote memorization or just the skill-based learning that sometimes happens, particularly in algebra courses. And we wanted a greater emphasis on how students communicate mathematically. How do they talk about the graphs? How do they present graphs? How do they interpret them and design them? And how do they convert from different styles of explanations and still stay accurate? And so we have our current round of evaluations from our fall semester underway, and we are planning on continuing this into the future, but these are our assessment plans and what we're hoping to do to measure whether our students are meeting those course objectives. And so I think we've got a little bit of time left, is that right? And so we wanted to open up to any questions that our audience and attendees had. So please use the question and answer button down on the, if you get here, there's a question and answer thing that you should be seeing down at the bottom of the shared screen. We'd encourage you to go there to ask your questions.
I have a question we could talk about.
Okay.
We got this course approved to run at 6 credit hours, which I was a proponent of arguing for that because I thought it would be useful, but also because I thought they would never allow it, and that this would be a good way for us to get 5 credits. But
Sure.
The first summer I taught this course online with 6 credit hours, I had a 92% pass rate, which is off the charts for an online course. I don't think I've ever had an online course do that well. And the students really took advantage of the extra time, and they functioned well with the group projects. Even though it was an online course, it was really fantastic to watch. And my success rates have been similarly good since then. And I think the extra time really, really helps with being able to dive into those co-requisite topics when you need to, and being able to spend some extra time doing some extra examples in class.
Yeah. And getting their hands dirty as well. They have more time where you are available for them to play around and work with the math as well.
Yeah, you can do lots of class activities, get discussions going, have group discussions. And that interaction time is really valuable. When you try to teach the regular quantitative reasoning course on a 3 credit hour schedule, I find myself really struggling to do everything. So.
Yeah.
Any questions from our audience here? Feel free to chat in or click on the Q&A box down at the bottom of the screen. One thing that I was going to note too, just in working with different schools through Hawks, we've seen these co-requisite style courses find a lot of success, but there are different ways that you can always implement it too. I know you were talking about integrating the algebra review. I've seen schools also just spending extra time on these credit level topics instead of the integrated review. So there's all sorts of ways that you can kind of implement these co-requisite style courses, just depending on what's best fit for your students and where you want to spend time on topics. Oh, let's see, we've got a question here.
Yeah, we could.
Someone said, do you want to go back over the financial problem?
Yeah.
So
should we do the insurance one? Let's do the insurance one. That's more interesting.
Go ahead, Max.
Okay, so let's see here.
That's your first one.
Yeah. You can think of insurance like a gamble. The unfortunate part is that when you make the insurance bet, you win when something bad happens. So you buy fire insurance and your house burns down, you win because you don't have to pay the cost of that incident. If your house is damaged in an earthquake like we had this morning and you have earthquake insurance, you are happy that you made that bet. On the other hand, if you pay your insurance like I pay my car insurance every month and I never crash my car, I'm just donating that money to the insurance company, or at least that's what it feels like. Okay, so how does this factor into expected values?
I'm going to go ahead and go into the next one if you want.
Yeah, go ahead. So let's talk about a life insurance policy. This life insurance policy pays out $100,000 if the person dies. We're talking about offering this life insurance policy to someone who is 55 years old, non-smoking, female, and moderately good health. Well, the question is, how much do we need to charge per month to make this a good deal as the company? And the way to do this is start by computing the break-even point, which is the point where the expected value is equal to 0. And then look at some mortality rates. How likely is it that Janice is going to die this year? If Janice dies this year, we pay out a $100,000 policy on a person who's only paid 1 year worth of premiums, and that's not a very good deal for us. So we need to be pretty low probability that she's going to die. And it turns out within the next year, it's only 1 in 500. Okay, so the probability that Janice dies in the next year is only 0.002. And when you compute the expected value, you end up with a payment of, I guess this is a yearly payment, isn't it?
It is.
Of $200. Now, for students in a course like this, you might say, okay, well, the annual cost of this is just going to be $200, and that's what you're going to pay every year. In reality, the cost would probably be different because you'd use some sort of probability density function where you might use integration to figure out how the probability of dying is going to increase over time. But you can still say meaningful things about examples like this in a class that involves no calculus.
Right. So just to finish the example, we found that break-even point, but insurance companies are in the insurance business because they want to make money.
Of course.
And they don't want to just break even. And so they typically charge some margin on the profit, which 20% at the time I did this looked to be the going rate at which they did that. So they tack on 20% and they're going to charge her the $240, which equates to $20 a month if they were to charge her on a monthly rate as well. And so that's an example of using probability. And again, we're skipping all the calculus in our calculations. We're not doing any integration. We're not worrying about the students being able to do that. What we're doing is giving them the idea of expected values, putting it into a context that matters, and allowing the students to work through using arithmetic, a little bit of algebra to find a meaningful solution.
So a big motivating question that I like to think about with examples involving expected value is how you consider the positive benefit in the case where you do buy insurance. For example, if you buy car insurance, you're paying this monthly premium. If you crash your car, the insurance company is going to buy you a new car. I think it's logically correct to think about the probability of crashing your car and the positive economic benefit of the insurance company paying that off versus not buying the insurance, which costs you nothing, and then consider the economic, what's the opposite of benefit? Deficit. Cost incurred if you actually crash your car and you have to pay for it yourself. So I think people think about paying their insurance premium and then getting a new car when they crash their car as a neutral transaction. Nothing happened. The insurance company just fulfilled their contract. But I think that represents a gigantic economic benefit to the policyholder in that case.
And again, that goes back to you're actually gambling against yourself with most insurance policies.
Yeah.
Which is why we like to hit it pretty hard with my students anyway.
Mm-hmm. And the assessment question that we used about cell phone warranties was particularly relevant because all of our students have cell phones these days, and many of them are buying these warranty policies without properly understanding them. Mm-hmm. So that makes a good question to use as an example or even a project.
Right. Absolutely. All right. Well, I think we're pretty much out of time.
Yeah, I think we're right at time here. Thank you guys again for presenting today, and to all of our attendees who joined. If you have any questions for us at Hawks, you can email us directly. We're at marketing@hawkslearning.com, and we'll be emailing a link to all of the recorded sessions and everything that we have for the week at the end of the summit. So just be on the lookout for those, and I hope everyone stays safe and healthy this week. And thank you again, guys, for presenting today.
It was our pleasure, and thank you everyone for watching.
Yeah, thank you.